we're going to describe the relation between two variables. Okay, some of the objectives for this section is we're going to draw and interpret scatter diagrams, look at the linear correlation coefficient, determining if there is a relationship between two variables, and then the difference between correlation and causation. Okay. Key definitions that you would want in your notebooks is the response variable and the explanatory variable. Response variable can also be referred to as the dependent variable, and the explanatory, the independent variable. For instance, club head speed of a golf club and the distance the ball carries. Well, in this case, the club head speed would cause the ball to go further, so the response variable would be the yards it carried, and the explanatory variable, which is the independent variable, would be the club head speed. Scatter diagram, and I'll show you an example very soon. It just shows the indivisible of each data set is presented on the graph. Here an example of a scatter plot. It's just basically a plot of scattered dots of the response and explanatory variable. Okay, we're going to come back to this. You're going to come back to this and really use those data points to show and how we can interpret different things. So if you look here, those particular values, x and y, your depth, which is your x or your independent variable, and in this case the explanatory variable, and time on the left and the y-axis. Various types of relations in a scatter diagram. Pause it and look at them at your own pace and discretion. Okay, just like you've been dealing in your algebra classes in prior years, positively associated would look like a positive slope. As x increases, y increases. As x decreases, y decreases. Where negative associated is if you would have one positive value and one negative value, and vice versa between the two variables. Now, the linear correlation coefficient seems like a lot here, but basically this formula is a little cumbersome. We're not going to actually do this by hand. The TI-84 has the full capabilities of doing this. It's just I do want to point out that this is where they're getting it from. If you recall back to Unit 3, the standard deviation, the mean, it's all coming from those particular formulas to really determine the strength of the linear correlation of the positive or negative correlation between the two variables. And we denote it by small letter r. Now here are some properties. Key is that -1 to 1, where 1 is positively associated and -1 would be negative associated. There's really no variation off a line. Closer to 1 or -1, the stronger it is. 0, there would be no linear correlation. Now it doesn't imply no relation, just no linear relation. Okay, here's an example of a positively linear correlation. Now, that formula that you had a couple of slides back showed how to get the linear correlation coefficient. We're going to look at it using the calculator. So here's the data points that was before. I'm going to bring up my calculator here as you do the same. A few points. For us to identify the correlation coefficient, we're going to need to see and turn on the diagnostic. So the first thing you do is second 0, which is catalog key. And then you can either scroll down to diagnostic on or press this matrix key, which is the D's, and then just scroll down to diagnostic on. Once you have diagnostic on, we're done. Now what you're going to do from here, and this is very important going forward, you're going to press stat. And I have the key press history up here for you to identify these. And in stat, we're going to edit. So we're going to put these into what we call a list. And now you've probably done this in Unit 3 with the one variable stats. Now I've already, to speed up time, I've already put these into two lists. I have L1 and L2. Now it doesn't matter where you enter these, just know where you have the independent and dependent variables. Once I have these into two lists by just listing these, I'm going to go back to stat. I'm going to go to calculation. Now, if you look here at number 4, it's linear regression, and that's where we're looking at. We press enter. Now mine looks a little bit different than yours. Yours just probably says linear regression. You're going to do second L1. Now I'm not going to do it on mine because I already have L1, L2. But if you do second L1, comma, second L2, you'll be able to bring it up. I'm just going to X out, X through, enter, and then here we go. We'll get to A and B in a minute, but you have R squared and you have R. We're going to look at R right now. Now we're going to come back to R squared eventually, but right now we're going to look at the linear correlation coefficient, which is this number right here, which is 0.773 rounded off to the thousandths. So if we come back here, look how much work we would have to do if we had to do this just using the formula and doing it without the use of the calculator. And that's exactly what we got, 0.773. So take notes on it, pause it, and kind of use that as your guide going forward. Does a linear relation exist? Here an example of what you would need to do to determine. A lurking variable is a variable that's related to both the explanatory and response variable. Things that we don't see that could be a cause of something that we necessarily evaluating. You can read here the example here. Ice cream sales and crime rates have very high correlation. That doesn't mean the more ice cream sales you have, the higher the crime rate. It happens that way just because there could be a lurking variable, in this case, temperature. And that is 4.1. It's an introduction just to the correlation. Now we're going to take that and use the least squares regression line in 4.2, which will allow us to evaluate data going forward.